Spring has sprung, the grass is riz. Just wanted to quickly mention how spring works, because I asked my GSIs. I said, you know how spring works, right? They all nodded. And I said, so when did you learn that? And one of them said, I think it was 4th grade. The other said 7th grade. If you don't learn in 7th grade, you'll never learn, because we don't teach this in any class other than this. Some people teach it in Physics 7. I do when I'm teaching it. Here's the Earth. And you notice the axis of the Earth is tilted. Tilted with respect to what? It's in space. Tilted with respect to where the sun is. So here's the sun, far, far away. The sun is actually bigger than this. And I'm shining the light on the Earth from the sun. You'll notice the light is shining straight down, and 1 square inch of light hits 1 square inch of the Earth. Except up here, where the light spreads out, and 1 square inch of light gets spread out over 2 square inches. So the light's getting spread out up there. It's less intense. It's not, 1 kilowatt per square meter when the sun's overhead. When the sun's over there grazing, that 1 kilowatt gets spread out over many square meters. And so it's not as hot. So it's this tilt of the Earth that causes the seasons. When the Earth is tilted this way, you notice the northern hemisphere is tilted away from the sun? So when the sun is hitting North America here, it's tilting there. And so it's not very hot. This is winter. But at the same time, the sun is hitting straight down here, right head on. It's summer in the southern hemisphere when it's winter up here. So how do we ever get summer? Well, this goes all the way around the sun, way over there. It's still tilted the same way. Now it's on the other side of the sun, and the sun is like this, and here's the sun. And now, look at that, the sun's overhead. So this is summer. Except down in Australia, where when it comes around, it's very grazing. It's winter in Australia. So these are the seasons. Now there's a little irony here, because it turns out that when it is winter this is summer. This is summer in North America. When it's summer in North America, that's when this Earth is way over there, and then it swings around. It doesn't go in a perfect circle. It goes in a slightly egg-shaped orbit called an ellipse. And the ellipse gets closer to the sun on one side than on the other. So here's the orbit. I'll exaggerate it. It's elliptical. And here's the sun, and you're not moving in a circle. And here is when we're closest. Called perihelion, when you're closest. This is when you're far away. It's aphelion. Turns out that U.S. winter is when we're close. Of course, it happens to be Australian summer. And U.S. summer is when we're far away. That's because the difference in distance is only a couple percent. Really small difference. But the tilt is a big effect, because the sun coming in at a grazing angle means that light, instead of being in a square meter, is spread out over 2 square meters or even more. If you're up at the North Pole, I mean, look at it. Here we are in the winter at the North Pole, and here's my sun. And take a look at how much sunlight is getting to the North Pole. None. Because it's behind. It never moves. It's behind the shadow of the Earth. So you have 6 months. When it finally comes this way, then the sun is grazing on it. Just barely grazing. That's sunrise. When the Earth moves over on that side, now you have the full summer. Full summer is still not very straight on. The reason it's so cold up there is because the sunlight is spread out so much, whereas on the equator, it comes straight down. So I want you to all know that. Part of the reason I want you to know that is in case they have TV crews come around and interview people from this university sometime. They do that at Harvard. And they ask Harvard graduates, what causes the summer? There's a famous film made of this, in which the Harvard graduates say, oh, summer. Oh, that must be when we're closer to the sun. Yeah, it's when we're closer to the sun. And they said, well, why then is it winter in Australia? Oh, winter in Australia. I don't know. So then they started asking some Harvard professors. Oh, winter in Australia. I don't know. Really embarrassing for the whole school. But it's because we don't teach it. So, end of that little story. It's spring. Spring means we're right at this point. This is the first day of spring. We're not that way, tilted away. We're not tilted towards. We're just, the sun is right over there. Of course, the Earth's moving around, not the sun moving around. Okay, tritium. Tritium was in the Daily Cal on Tuesday. I posted a little note on the bulletin on our website about the tritium with a few links. It was in the news. It was a fascinating article in the Daily Cal about the tritium. They asked to interview me, but I got the message too late. The tritium is not used in two things in Berkeley, as near as I can tell. One of them is in my wristwatch, and the other is in exit signs at Berkeley High School. So they actually have a tritium display in these exit signs. I didn't know that. And then I started looking up tritium exit signs, and I find there are places where you can buy one. You could buy one. You want a tritium exit sign? You can go buy one. It's $139. What else do you have to do with that kind of money, right? So go buy a tritium exit sign, and it's the same thing. The power goes out, everything's shut out, it's the middle of the night, there's no power, you're stuck in the middle of Berkeley High School. I don't know what you're doing there at midnight, but the lights are all out, and the exit sign will stay on because it's using the radioactivity of tritium. Remember, tritium has the lowest energy electron emission of any element. Radioactivity doesn't get out of here. I regard it as completely safe. That's why I wear this watch. Is it safe in these exit signs? Well, if you look at the article, you find there's this discussion. And several of the people who are in the middle of making this discussion obviously don't know anything about tritium or about radioactivity. There's one person who does. It's City Council member Gordon Wozniak. Gordon Wozniak was an LBL physicist before he decided to go to a higher calling. He was a superb physicist. And then he decided to do public service as a city council member. And if you look at his quotes, they all make sense. They're all correct. You look at the quotes of everybody else, it's all this frantic thing about, oh, the worst thing that could ever happen is what if this gets into a landfill someday? Ooh, wouldn't that be horrible? Radioactivity buried underground. What if it leaks out? In the signs, there's actually tritium gas. Tritium gas. So what if it leaks out? It gets into the environment. Of course, then it spreads out so much. The amount of tritium in here, the exposure you get from this leaked tritium, as near as I can tell, I've done a little bit of checking the numbers. It makes it basically completely safe. But besides, tritium is hydrogen. And so the hydrogen would very quickly rise up to the top of the atmosphere. So anyway, there's this little thing about tritium. If you look at those articles, I think you will find it remarkable how much you understand them. There will still be some questions, but the key thing is there will be questions. You will have questions to ask rather than just look at this stuff and say, oh yeah, tritium, oh, that sounds scary. Okay, that's the tritium gas. Let me do this little video demo here. So if we can, this is my camera. This is the camera that I use, photograph lions and tigers and bears and other things. I took it to Paris and photographed my daughter and her then boyfriend dancing in a dark nightclub, and I was able to do it. Because what this has in front of it is this little red thing here. See that little spot? You might not even notice it on your camera. This little red piece of plastic. What it is an infrared flashlight. So when this senses low light, and I have it in the special infrared mode, night setting, then this will shine like a flashlight, but you won't see it. The camera will, because the sensors of the camera, unlike the sensors in the retina of your eye, are sensitive to the infrared. So it'll pick up light. Then it'll put it on the little video display as a white light that I can see. So this can see in the dark. These little red things are kind of interesting. You'll notice them on your TV remote control. When you push a button to change the channel, what you're turning on is a little infrared flashlight. You know how you have to point it at the television? You're pointing the flashlight at the television. It's in the infrared. There's an infrared sensor. When this light goes on, it does something. How does it know what to do? Well, the flashlight is not just on and off. The flashlight goes beep, 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 beep in a pattern. The sensor picks up this pattern and says beep, 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 beep. Ah, that means channel 11. So these things are coded, and it's done through infrared. So is this thing on now? My camera's not on now. Let me turn the camera on. Oh, there you are. Okay, how about turning all the lights off? Oh, there, see you there? You notice you're in black and white? That's because it's picking up the infrared. So, but the people in the back are too far. Whoops, don't want to turn it off. Let me have it. There you are. Whoa, zoom. I don't like these electronic zooms. They're too fast. Let's have all the lights off in the room, please. Now, you see there are some things glowing there? Infrared things glowing. But in the front, we're getting to where the flashlight is. And let me get up really close here for some people. Notice the red eye. Beautiful examples of red eye for people who are looking right at the camera. Okay. Okay. Now, gee, I should go close that door over there. Let's make it really dark in here. Oh, that's... Okay. You can see why this would be useful to the military. So let's see, what do we have here? Okay, so I wish it were darker here because, you know, it's that light that's causing the problem. But obviously, you can't both see the screen and have the light all turned out. So this is my, now just imagine a classroom of people salsa dancing. So this is for seeing in the dark. It's not really dark. Okay, we have the lights back on now. So there are several types of see in the dark devices. This is the ordinary infrared flashlight, sometimes called the near IR, NIR, near IR. Near infrared means the infrared is not that far away from the visible. Okay, typically a wavelength just a little bit longer than red light. You can't see it, but it's near the red light. The far IR, sometimes called FIR. FIR sometimes stands for far infrared, sometimes it stands for forward-looking infrared. That's usually FLIR for FLIR. FIR, the far infrared, is the infrared light that's 20 times longer wavelength. This is the light we emit just from being warm. And those require special detectors. The reason they require special cameras, I can't buy one for under about $3,000. The reason they require a special thing is that they're warm too. So they're emitting light. It's like owning a camera where the inside of the camera has a light bulb in it. The camera is glowing. How do you take a picture with a camera which has a light bulb on the inside? Exposing the film all the time. They do this with tricky ways. One is to cool the inside. They do this with liquid nitrogen. The one I used at the Mexican border had liquid nitrogen cooling to keep the camera insides from emitting light by cooling it down. Another way they do it, which is a more modern technology, is they have the sensor, and the sensor is surrounded by this light from inside the camera. And they measure the intensity of the light. Then when they open up the shutter, a little bit more light comes in from the person. And that changes the brightness of the spot by a tiny little bit. They measure that and subtract the difference. And that's the light coming in. That's a much more advanced technology. It's for some, they have some scopes now. They're rather expensive. That will work in the far infrared. But that's how they work. The third kind is simply an image intensifier. So these are the three kinds: the far infrared, the near infrared, and the image intensifier. Image intensifier is sometimes called a starlight scope. It was first used in World War II. And it just takes advantage of the fact that there's usually some light around. You can't see it, but that's because your pupils are so tiny. Birds with bigger pupils, cats with pupils that aren't little tiny circles but open up this way wide, can see things at night better than we can, largely because of the design of the eye. It's designed for night. They don't like to go out during the day because everything's too bright. My dad was that way. He used to wear sunglasses during the day. It was fine at night. What you need to do is get more light in. Now, there's a thing you could do. You could build an artificial eye that had a nice big opening, lets in lots of light. Then it would be able to see it. Then you make a little projector onto a little TV screen, and you can see it. They do this now with devices that you can actually wear on your head. They have a little TV camera, a little amplifier, and then they display it right in front of your eyes, a little magnifying glass there so you can focus in close and see it. And you can do it in stereo. So they actually sell these things. They're basically sometimes called starlight scopes, but they're also called image intensifiers. What they do is they take an image of the light and simply turn up the brightness. And there are lots of different ways that these things work. I know a lot of the details. They're not that important to you, but they use this electron multiplication. Let me turn this thing on. And again, I think I'd like the lights down for this. I have a light bulb in here. And I'm going to turn up the electricity to make the filament hotter and hotter and hotter. I think it lights down even more. Let's make it dark in here, because this thing can actually get pretty. So what I've done here is the light comes from this light bulb, which you notice is sort of orangish. That's because it's not that hot. And when you start warming things up, first they turn orange and sort of reddish, and then they become white hot. And then blue hot is the hottest of all. Normally, painters associate blue with cool, but that's because we think of blue as being water. In fact, a blue flame is the hottest of the flames. So now I'm going to heat this up. And what we've done is we've set up something here that works the same way as a prism does. It takes the light of this lamp and spreads it out. So we have a lens to focus it on this white screen on the front. There's the screen. But now the light, instead of coming from the flashlight, is going to come through this thing that does the same thing as the prism. It's actually not a prism. It's called a diffraction grating, but it does the same thing. It breaks the light up. So let me turn up the light. Now you're beginning to see the colors over here. Kind of hard to see. But at this end, there's the red. And then there's some green. And you really don't see much in the way of blue. You might see it better if I turn off this ultraviolet lamp, which I might be able to do in the dark somehow. Now I'm going to turn up the heat by putting more electricity through this filament. And you'll see the colors. They'll be the colors of the rainbow. Oops, I got to turn it the right way, I guess. There we go. Well, there we are. That's pretty bright now. So what you see now is the light, first of all, doesn't seem as yellow, as orangish anymore. Because it's hotter, the wavelength is getting shorter. That is, the frequency is going up. So now we're getting a mixture of blue and green, and you can see that here. You can see that here's the red, a lot of red, but now there's a lot of green too. In between it's sort of yellow, over here is blue. These are the colors of the rainbow. They're not all the colors you can perceive. Why is that? Because what your eyes do when they perceive color is they will measure how much red there is, how much green there is, and how much blue there is. And if I were to take this light and instead of putting this spectrum, just put up 3 lines, one there, one there, and one there, your eye would look at it and couldn't tell the difference. Even though there's just 3 spots of light instead of the continuum, your eye couldn't tell. Because your eye has only these 3 color sensors, and if it gets the same amount of red as it would here, the same as green and the same blue, then when they're all mixed together, your eye would say, oh, that's white, even though it's not. So this is the spectrum. Out over here, this is the violet end of the spectrum. And out over here is the ultraviolet, which you don't see. I don't have, this isn't set up so I can, what I'll do probably next week is set this up again, but have a sensor over here that can see the ultraviolet. These rocks, I could put a rock here, but it's not quite sensitive enough. Over here is the infrared, which you can't quite see. But I bet my camera could. Interesting thought. Oh, no, the trouble is the camera will turn on its own flashlight, so that won't work. Okay, so this is the colors of the spectrum. I can have the lights back on now. So, once again, I want you to really appreciate you are emitting far infrared. The warmer you are, the more you're emitting. I hope many of you have done the experiment that was required for today's homework. do it next week. That's okay. Do it over spring break. Now, this is going to lead into the greenhouse effect and global warming. That's where I'm headed with this, but we're going to start by sleeping out overnight in a sleeping bag. And this leads directly to the issue of global warming. I don't know how many of you have slept out on an open field at night in a sleeping bag or not, get up in the morning and you are covered with dew. How many people have had that experience? How many people know that if you sleep out in that same field overnight and there's a tree over there, and you sleep underneath the overhanging of the tree, you will not be covered with dew? How many people knew that? Not so many. See, when I go out like that, I really prefer, I mean, you know, it's a real toss-up, because if you sleep out under the tree, you don't see the stars as well. At the same time, you don't get soaking wet. Now, why is it you don't get wet? You should do this. Next time you go out, you know, do a controlled experiment. Have your friends sleep out in the field, and you sleep under the tree, and see which one is soaking wet in the morning. What happens is this. When you are, here's the ground, and there's you in your sleeping bag, and at night, the sun is no longer shining on you. You are emitting radiation because you are glowing. You are glowing in the infrared. That means you are losing energy. Your electrons are shaking. When they shake, they emit waves. When they do that, they lose some of their energy and they slow down. So you are cooling off by heating. This radiation can heat something else up. If you go next to a heat lamp or a light bulb or a close friend, you feel their warmth. It can warm you up because that radiation comes in and is absorbed by your electrons. You are also emitting, however, and so you are losing energy. So here at night, here's the sky. There's no sun up there. You're basically losing energy to the sky. You are emitting this radiation, and therefore you are cooling down. And because you're cooling down, the air, it turns out, doesn't emit as much, even though it's the same temperature. Well, it's not the same temperature as you, but it will not emit as much simply because it's so thin that it doesn't emit very effectively. There just aren't enough, not enough density of electrons there to emit the temperature that's there. So this stays relatively warm, believe it or not, as you cool off. The result is, if there's water vapor in the air, it tends to condense on you in the form of these dew droplets. Against the cool you get the dew droplets on you. Suppose there's a tree over here. Okay? It's also emitting radiation. It, too, will have dew on it if it's emitting this radiation. It emits it in all directions. Aha! Suppose you sleep over here. Now you are emitting radiation, but you're absorbing radiation from the tree. As a result, your surface will not cool off as much. And because of that, dew will not form on you. You know, this has given rise to all sorts of legends about this tree protecting you from the dew falling. Well, the dew is actually coming from the air right around you, but if your surface doesn't cool quite so much, it'd be quite warmer to sit under a tree. One of the coldest places I've ever been was out on the Sahara Desert a year ago, December, because the sky is so clear. When it starts cooling down, you cool off very rapidly. If there are clouds up here, it doesn't cool so much. You know, in third grade, your teacher will tell you, well, the cloud acts like a blanket. But what's really going on? What's really going on is you are emitting as much radiation as ever, but the cloud is also emitting radiation back at you. So you don't cool off as much. This is the key science of the greenhouse effect and all of our concerns about global warming. Let me show you how that works. I said the atmosphere doesn't emit that much, doesn't absorb that much because it's not very dense. But let's consider the entire atmosphere, going all the way up to, well, it goes very high, but the scale length is about 8 kilometers, 8 kilometers down to about 1/3. So let's just consider the bottom 10 or 15 kilometers. Here's the Earth, and here's the atmosphere. And the atmosphere is thick and spread out. But let me just pretend it's just one thin layer, just for the purpose of illustration. The fact that it's spread out doesn't make much of a difference for this argument. Now here's what happens. Light from the sun comes and heats up the Earth. The Earth, during the nighttime, but also during the daytime, is warm, so it emits radiation back. If the Earth were cold, then it wouldn't emit much back. And so if the Earth were cold, listen to this, all right, please wake her up. Whoa, whoa, wake up. Wake up. This is a tricky thing to understand. Don't want you to miss it. If the Earth were cold, the sun comes in, makes it warmer. You think it would lose that radiation, but it doesn't because it's cold. You only emit things when you're warm. So you absorb the sunlight no matter how cold you are. You always absorb that, but you only emit it if you are warm. So the cold Earth doesn't emit anything. It just absorbs, gets warmer, 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 warmer. Finally, the Earth gets to the point where it's so warm that it's emitting as much radiation as it's absorbing. At that point, the temperature stops changing. Suppose it were to get hotter. Suppose it accidentally somehow got hotter, maybe a nuclear bomb or something. It gets hotter. Well, then it'll emit more radiation that it's getting in, and it will cool down. In fact, this is a nice calculation we do for the physics majors. What you do, there are some physics majors here, you might try this. You take the sun, and it's 6,000 degrees Kelvin. And here's the Earth. This is emitting radiation in all directions. Some of that radiation hits the Earth. That will warm up the Earth. You can calculate how much of that radiation will hit the Earth. It'll get warmer and warmer and warmer until it emits as much as it's getting. At what temperature will that happen? The answer turns out to be about 280 Kelvin. So the Earth warms up to 280 Kelvin. That's somewhat below freezing, by the way. But that's what the Earth will heat up to, if not for the greenhouse effect, which we're coming to. So just based on the fact that the sun is shining on it, it warms up until it emits, gets it up to about 280. 280 would not be warm enough for life on Earth, and this is where the atmosphere comes in. It's like sleeping under a tree. So here we are. Here's the sun, and this warming up to 280. But now watch this. It turns out that a good fraction of the radiation, in particular the far infrared radiation, the FIR that you don't see, doesn't get through the atmosphere. Key point. FIR does not, well, some of it does get through the atmosphere. Let's put it this way. Actually, a little does. And that's going to actually prove important. So what about the FIR coming from the sun? Does that get through the atmosphere? Trick question. There isn't much FIR from the sun. The sun emits mostly visible light, which is why our eyes are sensitive to visible light and not FIR. So that's one of the reasons. So there's not much FIR. This is visible light coming in here. Mostly red, green, and blue, with a little bit of UV and a little bit of near IR. Okay, that's coming in, heats up the Earth. Now the Earth heats up to 280. It emits FIR, because that's what we're emitting in this room. We can't see ourselves glowing because we're only room temperature. So we emit FIR. So the Earth so this emits FIR, but FIR doesn't go through the atmosphere like I drew here. It gets stopped by the air. This is the greenhouse effect. In the news every day, going to be more and more in the news as this becomes more and more of a global issue. It's hotly debated right now, coldly debated. I don't want to mix metaphors. Okay, so it gets absorbed in the atmosphere. That means we're not going to cool off. Because the atmosphere is like the tree, it emits it back to us too. Well, it also emits it back to space. So this is the key diagram. It's in the book. Let me go over it again. Absolutely important and going to be critical. Our future, what kind of fuels we use, will have to do with the greenhouse effect. This is becoming more and more of a national issue because many people believe that the world dumping of carbon dioxide into the atmosphere could affect this whole process and change the temperature of the Earth. And many people believe they're seeing this already in the data. Warming of the Earth from the world burning of fossil fuels. Here's how it works. Visible light comes in. It emits it to the atmosphere. The atmosphere sends some of it back and some of it out to space. This whole thing warms up until the amount going back to space here equals the amount coming in. When these are equal, then there's no more warming. So let's assume that this radiation is roughly equal to the sun radiation coming in. This is a really subtle argument. I'm not going to ask you to reproduce this argument. This is beyond what you need to know, but you will impress the hell out of your friends if you watch this webcast over and get this argument right. The sunlight comes in. We emit far infrared into the atmosphere. The atmosphere emits it both ways, up into space and back down. It gets warmer and warmer and warmer. Basically, the atmosphere gets up to 280 Kelvin. So that this radiation reaches that radiation. When they're equal, then it no longer warms up. But look what happens down here. This radiation is equal to sunlight. It has the same intensity as sunlight because they're balanced. The far infrared radiation of the atmosphere equals the radiation of sunlight. Isn't that a neat result? But it's emitting it not only upward, it's emitting it downward. That means here on the ground we get the radiation not only of the sun, but we get the far infrared radiation of the atmosphere. And this amount equals the amount from the sun. We are warmed by the sun, but an equal amount of warming on an average over the day comes from the atmosphere. That warms us up. That is what is called the greenhouse effect. Because the same thing happens if you build a greenhouse with a glass cover. The sunlight comes in, traps the heat on the inside. So we get twice the radiation, and that warms us up from 280 to something like 320. Question? Yes, Zach. Freezing water is 273. Oh, maybe you're right. It's lower than that. You're right. Thank you, Zach. This was like 250. Okay, just get my numbers right. Absolutely right. I think if the book, I'm sure, has the right numbers. Thank you. Okay, so what happens is because the atmosphere is warming us, we get twice the radiation. That warms us up to the point where we can live. Without the atmosphere, it would be below freezing here on the surface of the Earth. Atmosphere makes life possible. Now comes to the modern controversy and the fear of what the greenhouse effect may be doing. When I gave you all this, I oversimplified a little bit. Not all of the radiation from the Earth gets absorbed by the atmosphere. A little bit of it leaks out. So our temperature under normal conditions is determined by the fact that we don't really get twice as much. We get a little bit less than twice as much. And that's what makes it nice and comfy in here on the Earth. In the Earth meaning here. In here meaning on the Earth. So some of it leaks out, and that's good. Because otherwise it would be too hot. Now we get to the global warming issue. The world is burning fossil fuels. Fossil fuels means that carbon dioxide in the atmosphere has been increasing to unprecedented levels. When we burn fossil fuels, we make carbon dioxide. Carbon dioxide in the atmosphere, not very much. I mean, the fact that plants live on it is amazing to me because it's only a few hundred parts per million. But that's enough for the plants to live and grow. Of course, plants kind of live and grow slowly. I wouldn't want to be a plant. I'd be kind of bored. Mostly you sit there and you breathe in carbon dioxide and you grow. Animals leverage this by eating plants. So you have plants everywhere, growing everywhere, and I go eating them all. And I get lots of energy, and I can move around and give lectures, which plants could never do. So they're doing this on, typically 300 parts per million. I mean, 1,000 parts per million is 1 part in 1,000. This is a third of a part in 1,000. That's what plants live on. But we are changing that. Humans have increased that already in this century. The charts are really extraordinary charts. It's not that hard to measure 300 parts per million. And Keeling of Scripps started measuring these things, and he noticed it's going up every year. In fact, you can see the seasons. When it's winter in the northern hemisphere, the carbon dioxide goes up more. And when it's summer, it doesn't go. So you're getting this oscillation. It's going up, and it's up to around, I believe, gone from 280 to, I think, 350, 360 parts per million. A really substantial increase. And many people believe that unless we put real curbs on fossil fuels, it's going to get up to 500 or 600 parts per million, within the next few decades. So carbon dioxide is increasing. Plants may like this. All this extra carbon dioxide in the atmosphere. Some plants thrive in the extra carbon dioxide. But the carbon dioxide winds up absorbing some of this light that should have penetrated the atmosphere. The carbon dioxide absorbs those frequencies of the far infrared that used to leak through. As a result, not as much leaks out. The atmosphere warms up more, sends more warming back to us, and the surface of the Earth grows warmer. Now, in fact, it's a little bit more complicated than this, because the surface of the Earth growing a little bit warmer tends to make water vapor evaporate, and that water vapor also absorbs the infrared that we're emitting. So this whole thing, I don't think we really understand the details yet. There's a great deal of research being done on this, and a lot of people making claims all the time. But this basic picture is correct, that for not getting overly hot, we depend on leaking infrared to space. Carbon dioxide tends to block that, and so should, sooner or later, unless something else compensates, like cloud cover or some other effect, if something else doesn't compensate, the carbon dioxide should cause warming. This is the cause of concern over global warming. Ozone layer, different problem. I don't want you to get those confused. Ozone layer was ultraviolet. And we have solved that one by cutting out the freons. It was relatively painless, it turned out, to cut out freons. For a while, you didn't get any spray cans. Then they invented other gases that are okay. Refrigerators and air conditioners had to have the gases changed. If you have an old automobile with an old air conditioner in it, you'll find you can't buy any freon except at exorbitant prices, because only a little bit of that is allowed to be produced. And so you have to use different gases in your air conditioner. That was relatively painless compared to cutting back on the carbon dioxide. We run on fossil fuel. Coal and oil and natural gas all add carbon dioxide to the atmosphere. What are the alternatives? Well, conservation is the best. Use less to get the same energy out. If you can afford a Prius, buy a Prius. Well, you can't afford a Prius. I can, so I got one. What about you? Well, the answer is cheaper Priuses. Cheaper. Well, where are they? They're coming. Don't worry. They are coming. I believe what Toyota was doing is putting out a super expensive one first so that the hybrid would get a good reputation. So everybody would covet one. That was really smart marketing, I think. The cheap ones are coming. You will all be driving hybrids using half the fuel you're now using in your automobile, within a decade or two, because this is the technology. I say I can look 20 years ahead. This one I see very clearly. In fact, 15 years ago, I was lecturing on the coming hybrid automobiles in all of my classes, because I knew they were coming. They're the obvious thing to do. Use your energy better. That's the best way to cut back on the CO2. Next best way is to find some alternative fuel. Maybe you take the CO2 that's in the atmosphere, use it to grow plants, and then burn that fuel. That has no net effect. This is the whole idea behind methane. Methanol, of growing crops that will take the CO2 out and then put it back. That's no net change. So that's a nice idea if you can do it. The best idea for that seems to be something called switchgrass, which President Bush mentioned in his recent speech on energy. Switchgrass is good because it grows really fast, grows up 12 feet in a year, then you cut it back. It's removed that carbon dioxide from the atmosphere. Now you let this ferment. That's the hard part, getting this to turn into alcohol, which you can use as a fuel. It's a technically solvable problem that I think will be solved. So this may be a real source. Other alternatives are nuclear, unless you really believe that nuclear is so bad because of the radioactivity that it is not a viable alternative. I understand that the U.S. hasn't built any nuclear plants in 30 years. China is now building 2 a year. That's okay. The scary part is that they're building several coal plants every week because they have a desperate need for energy because their economy is booming. And so why is the price of oil so high? Because they're buying every drop of oil they can at these exorbitant prices because they need it for their booming economy. So China and soon India will be the main producers of carbon dioxide in the world. It's getting very close. I think maybe, do you know when that transition is going to occur, Zach? 5 or 6 years. And then China will become the world's leader. The U.S., now the major polluter of the world, is not growing fast enough to remain the major polluter. If we in the U.S. cut back on our carbon dioxides, the problem isn't going to go away. It'll just be delayed by a couple of years. Because China is undergoing this enormous growth. Most of their energy is coming from coal, a little bit of nuclear. Their coal is not being done very cleanly because they desperately need the energy. And I personally don't feel I have any right to tell them not to do this because they have every right to have the same standard of living we do. I would love to leverage it to see them do this more efficiently and produce less carbon dioxide. But that is the problem. This is the carbon dioxide problem. There's probably no issue that is more important for you to know about and understand. Problem with nuclear, people worry about nuclear accidents. They worry about nuclear waste. You saw that in the video. What are the other answers? Well, you could have hydrogen, except hydrogen is not a fuel. It's a way of transporting energy. You have to make the fuel. How do we make hydrogen? These days, the main way we make hydrogen is from natural gas, by removing the carbon and turning it into carbon dioxide and putting it into the atmosphere. So hydrogen doesn't solve the problem unless you make it from electrolysis, which is more expensive, so nobody's doing that. So these are the problems. I want you to think about these, understand them, illuminate your friends who don't understand the subtlety of these issues. Right now, I see a lot of green people who, I resigned from the, usually I don't like to give you my own points of view on these things. I will depart from that right here because it was about 25 years ago I resigned from the Sierra Club. Very painful to me because I love the Sierra Club. I used to go hiking in the winter in the snow, go up there in snowshoes to the Sierra Club cabins. You know, took Sierra Club courses, wonderful thing. But I had to resign from it because they were opposing nuclear power. And I wrote to them and said, if you oppose, this was 25 years ago, you oppose nuclear power, we are going to be burning more coal and oil over the next foreseeable future. That's going to add carbon dioxide to the atmosphere. That's a greenhouse gas. It may lead to global warming. I wrote this letter to the Sierra Club 25 years ago and never got a reply. They went anti-nuke and 10 times the membership by their anti-nuke campaigns. I don't like nuke, but I saw the carbon dioxide. I didn't see it. Everybody saw it. Everybody who knew about this thing knew about this 25 years ago. Now it's finally becoming public. Now everybody is worrying about it, and there are articles by some very previously anti-nuke people. I think Christoph in the New York Times wrote this editorial. He's considered by the Republicans to be ultra left-wing, considered by the Democrats to be a little bit to the right. The left wing, he's sort of probably in the middle of the Democrats. He wrote an article called "Nukes Are Green" because of the greenhouse effect. So there's no more central important public issue. And that's all I have time to say about it. So we did springtime, tritium signs, video, dew, greenhouse, Stinger missiles. Let me just mention that in the military, infrared is really important because things that emit heat emit this infrared signal. And so one of the best ways to shoot down an airplane, it turns out, is to take your missile and on the front of it put a little thing that detects the infrared. Now you aim it up at the sky, and what do you see? Well, there's some birds there. They're not very hot. and there's some distant stars. They're hot, but they're so far away, they don't give you very much, and the atmosphere isn't emitting very much. But wow, this really bright spot, that's the exhaust of an airplane. So when you look up in the sky, the main emitters of infrared radiation are the exhausts of airplanes. So decades ago, the United States developed a way to handle this called the Stinger missile. You take an ordinary missile, on the front of it, you put a little detector, really simple detector. All it does is measure which side is warmer, there, or there. If that's warmer, steer in that direction. Now, whoops, that side's warmer, steer in that direction. Now, oh, they're all equal. You must be aiming right where you want to go. So that's all the Stinger missile does. It just changes the fins a little bit so that it's getting an equal amount of warmth in all four sectors. And that's all it does. People can carry these things on their shoulder. I remember with horror when the U.S. was arming this rebel group in Afghanistan called the Taliban with Stinger missiles. I remember watching this saying, you know, I'm not sure I want these guys to have these missiles. Fortunately, it turns out Stinger missiles are hard to maintain. But there are these Stinger missiles all over the world, and one of the real fears of terrorism, and this is being done primarily outside of the United States, you get one of these Stinger missiles, they can be carried by one person. One person just sort of sits and squats at the end of the runway. When the airplane comes off, the Stinger missiles don't have that big a range. I forget whether it's 10 kilometers or what, but it's mostly for shooting down helicopters and low-flying airplanes. The plane takes off, they shoot the Stinger missile. The Stinger missile, you don't have to aim it very well because it'll follow the heat and then go up the tailpipe and explode. And there's a really serious concern that this will be a breakout technology for terrorists. The reason that this hasn't happened yet probably has to do with two things. One is that the Stinger missiles are not that easy to maintain. You know, you got to make sure everything is clean and working. The second thing is it does require some level of sophistication. It's a little harder to get someone to learn how to operate a Stinger missile than it is to tell them, walk into the crowd and push the button. Or just walk into the crowd. We'll push the button. You just walk into the crowd. So this kind of terrorism is a bit harder. Third, airports look out for these things. You see someone walking around carrying a missile, you don't say, oh, it's probably just a harmless person. So this has not yet come about. But when, soon after 9/11, an airplane crashed in New York City on takeoff, everybody I know who knew about Stinger missiles went, oh my God, they had shot it down with the Stinger missile. Turned out not to be true. Okay, I want to get to medical imaging. So that's this here. To do this, I need to hook up the computer. Looks like it's hooked up. Let's see if I can turn it on and get some images here. So does that come up okay? See if you can project my computer. My computer's just switching, so don't panic just yet. Hey, we did it. Good show. Okay, I'll be showing you these things in just a moment. You know, back in the earliest day of the nuclear discovery, some of you are, no, I don't want to join Air Bears. Okay. I could. No. In fact, okay. Back when radioactivity was first discovered by Becquerel, when Curie found the radioactivity of radium, all these wonderful things going on, about that same time there was another discovery by Roentgen of X-rays. These are things that are produced, initially they were discovered just from, they can be produced by high voltage sources, by electrons banging in and suddenly changing. We talked about production of X-rays before. They are also produced in nuclear in nuclear decays. These X-rays come out. They are basically very high frequency light particles. Typically 1,000 times more energy per wave packet, 1,000 or 10,000 times more than you get in visible light. We'll be talking more about that next week. A property of these things that have such high frequencies is that they tend to go through a lot of matter that other things wouldn't go through. Visible light will stop on the surface of your skin. The X-ray will go right on through. It's because that frequency is so high. It's oscillating so fast that the electrons in your skin, they start getting to move up. But by that time, the frequency is reversed, and they're moving down. They wind up not absorbing much energy because you're changing direction. It's like trying to push a swing. And, you push a swing, woo, woo. And maybe someone else is pushing it the other way. And the swing gets higher and higher. But now you take that same swing and go, poor kid. Won't go anywhere because it's reversing so rapidly. So the X-rays, it turns out, go right through the skin. They tend to get stopped only at the inner electrons of some heavy nuclei. Things down there like calcium. That's not that heavy, but it's heavy enough. Because the electrons moving in the inner circles of the calcium are actually fast enough that they can absorb energy. So it turns out these things up here, carbon, nitrogen, oxygen, don't absorb much in the way of X-rays. Get down to calcium, and they do. Get even further down, and they really absorb it. One of the most famous absorbers of X-rays is lead. Where's lead? Lead is right. That's platinum. There's lead. It really absorbs X-rays just because it has those inner electrons. So what Roentgen discovered was he started looking at what do X-rays go through. He found that this photographic film, when you make X-rays, will fog up the film. So he put things in the way to stop it. And he found if he put his hand in the way, that the X-rays went right through the flesh, but not through the calcium of the bone. A fantastic discovery. Totally amazing. And this is what X-ray photographs do. It's a typical X-ray photo. The X-rays are stopped by the calcium. Okay, because they're stopped by the calcium, is that showing? There we go. Because it's stopped by the calcium, the film, when light hits it, the film gets dark. It's negative film. And so here the X-rays are going through, get dark film, dark film, dark film, dark film. Up in here, it's being stopped by the calcium of the skull, by the calcium. Oh, look at that. This has a little arrow here, probably pointing to the fact that that's maybe where I left my pointer for my. I think there's something interesting there. Anyway, there are the teeth. I see some cavities in the teeth. Cavities which the calcium has been rotted away, replaced by softer material that's more X-rays through, tends to be dark. You see the tooth X-rays. When they take X-rays of your teeth, what they do is they put some film inside your mouth. They have the X-ray emitter. You get a shadow of the tooth, but the place where the tooth is weak, where the calcium has been rotted away, replaced by organic material, X-rays go through a little bit more easily. Therefore, that spot's a little bit darker. So this was amazing. In fact, most people dismiss this. You can't see bones inside the human body. Broken bones, fixed bones this way. A truly revolutionary technology that was invented 100 years ago, over 100 years ago, X-rays. For a long time, this was the key technology that we used in medicine to see the things you couldn't see. When I was a kid in the 1950s, I used them in a shoe store. I love this thing. You put your foot in the X-ray thing, and you wiggle your toes, and you see all these bones moving around. You see how well the shoe fits. You also see a lot of nails in the shoe. I didn't know until I saw that. I didn't know there were nails in shoes. These days, we don't use nails in shoes because we've gotten super glue, so we tend not to use them so much. But still, we put in some metal supports which make your shoes go off in airport radio metal detectors. But the X-rays basically are stopped by the heavy elements like calcium and by the very heavy elements like lead and gold. That's why Superman's X-ray vision wouldn't work with lead because the X-rays just don't go through. Some people try to avoid X-ray detectors by putting lead in them. For your film, you can buy lead-lined bags. So you put them in the X-ray detector, and what do they see when this thing comes through? They see a bag that you can't see through. So what do? They ask you to open it up and show what's inside. Sometimes they'll ask you to say, okay, let's put the film through again. I've actually put some, only the most super sensitive film is exposed by X-ray detectors. I've done the experiment myself. I went through all sorts of airport X-ray detectors, carrying different levels of film, putting them in, then I developed them to see which ones were exposed. And I found that the fear is really overblown. But in principle, you can X-ray the bones of the body primarily by doing this. But there are other things you can do. And you use gamma rays. Gamma rays are even more energetic. They actually will get through thin pieces of lead and give you some image of what's going on the inside. Gamma rays proved to be the key for a project I was involved in to study the US Embassy building in Moscow, where we wanted to see whether the Russians had stuck any bugs inside the building to listen to our our people once the building was finished. See, we let them build the structure. And by using high-energy gamma rays, they had hidden these things so cleverly that an ordinary forward X-ray image would not have shown it. So we had to use something called a CAT scan. It was mostly done by a group at Livermore. A CAT scan, what it does is you X-ray it from one direction, or you could use gamma rays. Gamma rays are like high-energy X-rays. So let's say you do my head. Just the head on, front on. Then you do the head from this angle. Then you do the head from this angle. And then from this angle and this angle. And you do it from maybe 30 different angles. You get these 30 different pictures. You give this to the poor doctor and he says, ah. But you give it to the computer. And the computer goes in and says, let me calculate what the three-dimensional structure inside the head is. There's only going to be a unique structure that will give this images from every direction, called computer-aided tomography. The C in CAT comes from computer. Computer-aided. The tomography is photographing it from many, many, many different directions. It's like you're examining this apparatus. You look around it from all sides. And after a while, oh, okay, I see how it works. There's a lens in the middle. CAT scans take these X-rays or gamma ray scans from many different directions. The computer then figures out the structure that's inside. This is then put on a computer screen. And the doctor might say, okay, let me just look and see what's exactly in the middle. And the computer then will give him just the plot of what's in the middle. That's a CAT scan. And it's like an advanced X-ray. And let's see if I have a CAT scan here. Okay, so here's a CAT scan. And look at the detail of that. Even though the X-rays are only stopped a little bit by the blood, there is enough of the stopping that when you look at it from many different directions and then turn the computer to see only the things that are in the middle, that the brain begins to stand out. And you can see the nasal cavities here. And then you can see the brain cavities. I guess the guy's not very smart. I'm not sure what those are. You medical students here probably know a lot more about this. You see all the convolutions of the brain and the corpus callosum and all, amazing, absolutely amazing. If someone's developing a brain tumor, you can see where it is. A friend of mine developed such a tumor right in here. Those of you who are queasy, you now cover your ears for 13 seconds. So what they did to operate was they cut the bone here, they pulled the face off this way, they went in there, removed the tumor, took it out, put his face back on. My friend Stan Flatte spends every day of his life appreciating every day of his life. I'm sometimes jealous of him because he and his wife just appreciate life so much because they came so close to losing it all. Every day we should just say, hey, God, just being here, isn't this wonderful? Wow. I don't have a brain tumor. Okay. A little bit of protection. So that is called computer-aided tomography, or the CAT scan. They come up with these clever words. PET scan. PET scan is completely different. And it's also fascinating. I'm not going to be able to do all of these today, but let me just do the PET scan, because in the PET scan what they do is instead of putting radiation through your head, they feed you the radiation. You eat the radiation. When you have this radiation in you, sometimes it will go to parts of your body. For example, they give you a certain chemical that just happens to go to different parts of the brain, or they can give you iodine, it'll go to your thyroid. So you have radioactive iodine, it goes to your thyroid. But it only goes to the parts of your thyroid that are actually working. Now, the radiation they give you is a special kind, positron emission tomography. Positron emission. Positron is your first experience in this course with antimatter. A positron is an anti-electron. Positron. They will feed you antimatter. At least they actually don't feed you antimatter. They feed you typically fluorine or chlorine, radioactive chlorine, and then the chlorine will emit the antimatter. So you don't actually get fed it. But you make this antimatter then, and the antimatter comes out. What happens is, let's say here you are, and let's say there's some fluorine in here. And the antimatter comes out, or iodine here. I don't list any iodine ones. Since iodine, that would go to the thyroid. Let's talk about antimatter emission from the thyroid. When the antimatter is emitted from the nucleus, we'll be talking more about this in the next few weeks. The anti-electron finds another electron and annihilates. We'll be going over this. This is a lot to chew right now. It annihilates, emitting 2 gamma rays in equal and opposite directions. This is the process that's used. So you're fed this thing that's radioactive, emits positrons. The positrons don't go very far, but they're only in the region of the thyroid where the thyroid is active. It emits 2 positrons. Emits a positron that turns into 2 gamma rays. The result is you get 1 gamma ray going this way, 1 going this way. The computer picks it up. It says, there was a positron emitter somewhere on this line. Then there's another one here. It goes off. Gets picked up there and there. Computer says, somewhere on this line was a positron emitter. So you wind up getting all these different lines coming from different regions, but you wind up getting no lines coming from this region here. So the PET scan concludes that this region is dead. And you can see very tiny, small regions. What it does is it calculates all these lines. Now, it doesn't know where in this line it came from, but it's somewhere in that line. But you can find a region that's emitting no lines, then you know that's a region that is damaged. Or maybe overly active. So this is the key to a positron emission tomography. You need 2 detectors. It emits antimatter. The antimatter annihilates, makes 2 gamma rays. The gamma rays give you a line. And let me just show you a positron scan here. So there's a positron scan of the brain. The most fantastic of all, I'm going to have to leave till next time. But I'm going to show you a picture of it. You've probably heard about this because it is so unbelievable. In fact, I find it hard to believe. That's not a drawing. That's not a sketch. That's not art. That is an MRI scan, magnetic resonance imaging, used to be called nuclear magnetic resonance. They changed the name. You got to know this. They changed the name because they were dying patients who would not have this done to them because it had the word nuclear in it. So they changed the name to magnetic resonance imaging instead of it being nuclear magnetic resonance. And just that change of name is undoubtedly saving tens of thousands of lives of people who are so afraid of anything nuke that they would rather die than have their brain imaged in that way.